So folks, just to reiterate, I will be often turning the notes over to you where I say, hey, now I want you guys to work this problem. And I don't have a lot of time to do that, which is always unfortunate because I feel like you guys learn best by doing, but it takes you a long time to learn by doing, right? So one of the ways that we can sort of speed this up is if you're bringing printed off copies of the notes, it just allows you to do it faster. That way you don't have to write down the question and then start writing down the answer. You've got it right in front of you. Okay? So if I were you, if you didn't have your notes today, you'll live, right? But I would go ahead and go print them off now all the way through the rest of the unit. Okay? All right. So we are going to develop some properties for limits. And I mentioned this at the beginning of the section 2.2 lecture, that this is going to allow us to actually find values of limits without using this guess and test method of either the table or the graph that we discussed. We're going to develop a lot of the properties first, then we're going to go ahead and find the limits of two functions, and from there we'll be able to do quite a lot of work. Okay? So it's kind of interesting. I mean, right now I feel like we're building a little tiny snowball at the top of a hill, and we're going to build these properties, and then all of a sudden things will start snowballing quite a bit faster. Okay? All right. Let's first say that limits in a lot of ways behave as you would hope they would. Okay? They have a lot of nice properties. But in some instances they don't behave in the best of all possible worlds, and you got to be more careful. Okay? So what I'm doing right now is just highlighting those properties. Okay? So let's suppose we've got, we know the limit as x approaches a of f of x. We know that to be the number m. Okay? Just like we've written before. So for example, let's say I tell you that the limit as x approaches 2 of some function f of x is equal to 13. Okay? Suppose we know that. Okay? And suppose we know that the limit as x approaches 2 of some other function g of x is minus 3. What can we do based upon knowing the limits of those two functions? Well, it turns out we can do quite a lot by combining those two functions together in different ways. Okay? So if we know the limit of f as x approaches a and the limit of g as x approaches a, then we could find the limit of their sum. We could look for the limit as x approaches a of f of x plus g of x. Okay. And it turns out that limits behave very nicely with sums. Okay. We can rewrite this as the limit as x approaches a of f of x plus the limit as x approaches a of g of x, which would mean then that the limit is just the sum of the two values. Okay. Folks, I'm pushing you early on with notation because this class doesn't get any easier with notation, so I might as well throw you in the deep end now. Okay. What we're saying is that the limit operation, remember we said this limit operation is something we do to a function, right? If we're trying to do this limit operation to the sum of two functions, we can distribute the limit over the sum. So notice the plus sign was inside the parentheses here, right? And we've distributed the limit over the sum. Okay? That's a really nice property. You've seen that property show up in a lot of things. Does it show up everywhere? Does it always work? Okay. If you think of your square root operation, if I ask you to find the square root of 9 plus 16, does that equal the square root of 25? Well, let's check. Oh, sorry, it does equal the square root of 25. Sorry. Yeah. Does that equal the square? Does that equal? Excuse me, folks. Does that equal the square root of 9 plus the square root of 16?
No.
No. I cannot distribute a square root over a sum. Okay. Lots of things I can distribute over a sum, like multiplication, right? If I did 3 times 9 plus 16, I can distribute that 3 over the sum. Okay? And what I'm saying right now is limits behave similarly. I can distribute limits over the sum. Okay? So what we're saying here is that the limit of the sum is the sum of the limits. Okay? The book then gives you another property where it replaces this plus sign with a minus sign. I'm not going to do that. To me, that seems redundant. Okay? But it is true that the limit of a difference is the difference of the limits. Okay? So folks, this might seem like, what's the big deal? But here is an example where we can't distribute this operation over sums. Okay, so I'm clarifying what we can do. All right? The limit of a product, let me just tell you, is the product of the limits. Okay, so that's worth putting on a little note card. Okay, remembering that expression. Okay. What are we saying there? We're saying that if we take the limit as x approaches a of f of x times g of x, what can we do? We could take the limits of each one of those and multiply them together. And that would just give us the product of those two numbers. Okay. That's really nice. Folks, this first property about distributing an operation over a sum, that happens a lot in math. Distributing a property over a multiplication, that happens less frequently, I think. So it's really nice when we have that property. Okay. We've got a few more. Okay. This one's really a consequence of the second one. And it says if we look at the limit as x approaches a of a constant times a function, we can rewrite that as c times the limit as x approaches a of that function, which would just be, in this case, c times m. What on earth? Okay. Well, what did I do with that letter c, that constant? I pulled it out of the limit. Okay? This says that, oops, I got a little, folks, I'm going to have to switch these two on you. Sorry about that. We've just said that constants factor out of limits. If I gave you the expression 3x to the fourth power, and that 3 sitting inside the parentheses there, what can I do with that 3? I can factor it out of the parentheses, right? I could write it as 3x to the fourth power. There's an example where a constant came out of an expression. Can I always pull constants out of expressions? No. For instance, if I had 3x to the fourth power, could I say that's 3x to the fourth power squared? Could I say that's 3x to the fourth power squared? Heck no.
3 squared.
Right, it would have to come out. It can come out, but by a different property, and it behaves a little differently, right? Okay. Okay. So, folks, I apologize. These two are going to go together. I'm sorry about doing that. Okay. So if I look at the limit as x approaches a of f of x divided by g of x, what do you think? I think we can distribute the limit, but there's going to be one little caveat at the end. Okay? This is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, but provided the limit as x approaches a of g of x, which in this case is what I'm calling n, does not equal 0. Put another way, the limit of the quotient is the quotient of the limits provided the limit of the denominator isn't what? 0. Okay?
If it is 0, then the limit doesn't exist.
That's not necessarily true. Okay, remember your name again? Caleb just said, well, if the limit is 0 in the denominator, you just say the limit doesn't exist. And the answer is no. And that's actually what almost everything we're doing in the rest of this class is built upon. Okay? In some cases it won't exist, but in some cases it will. But you can't do it using this property. You have to do something else. Okay? So we'll talk more about that, but I'm about out of time, aren't I? Got 2 more minutes. We'll go all the way to the bell. Okay? All right. This is great. If I know the limit of 2 different functions, I've got all sorts of ways of combining them together to find new limits, right? But still, I don't know how to find the limits of any functions, right? That is, I've already said that if we can get to step 2 or step 3, we can keep going, right? But we still haven't gotten to step 1. So let's evaluate some simple limits. Okay? The limit of a constant is just the constant. Okay? The limit of a constant is the constant, regardless of the limiting value. Okay? We're going to prove this one in section 2.7 when we officially get to the definition of limits. But let me just show you right here on this graph. If this is the graph of f of x equals the constant c, and here's the limiting value a, what does it appear the y values approach as I approach a?
C.
They appear to be approaching c. That's what we've just said. Okay, the limit of a constant is just that constant. Okay. The next one is the limit of the identity function x as x approaches a is just the limiting value a. So the limit of the identity is just the limiting value. Let me say limiting as opposed to limit. So again, what does the graph of the identity function look like? Well, it's that it's that line that passes through the origin at a 45-degree angle, right? It's a very boring function, right? If you plug in a 2 into the identity function, it spits out a 2. If you plug in minus 28, it spits out minus 28. Okay? Well, notice, and again, we'll prove this one. So these 2 limits we're going to take on faith for right now, and we'll be able to develop everything we need for the rest of this chapter from these 2. Okay? But notice that as we approach a, what do the y values appear to be approaching? A, just the limiting value. Okay? All right, folks, we'll pick up with this next time. For those of you that got in late, first of all, I appreciate you making the effort to be here. Okay, I know that it was not easy to get in this morning. I have told the class that I will go ahead and provide 1 additional drop for the attendance quizzes, so that you're not penalized for this, because I don't want people doing something dangerous trying to get here to class. Okay, so I appreciate those of you who made the effort to be here, even if you couldn't get here on time, and I ask you to keep doing so going forward. Okay. All right. Remember my math due dates. 2.1 is due tonight. Okay. That's all I've got for you guys. You have a wonderful day. I'll stay and answer questions as long as you've got them. But if you didn't get your card, though, make sure you get it from me. Sorry. I'll come by and pick them up, but don't take them with you.
For the video,
Yes.
is that going to be where?
First of all, let me stop this one.